In lesson 2.1 quadratic functions, you'll learn how to graph quadratic functions, the parabola of quadratic functions in its standard form. You're also going to identify key characteristics to the graphs of these quadratic functions in order to graph a little bit more complicated quadratic functions. So let's begin first by looking at what a quadratic function is. A quadratic function is simply a function where the highest exponent is going to be 2. This is the polynomial form of a quadratic, ax squared plus bx plus c. And the graph of a quadratic is called a parabola. Now the shape of this again is the shape of a U. Now this U opens up or down depending on the type of value we multiply to the x squared. So in this situation right here, we have a reflection across the x-axis if our coefficient of x squared is a negative value. If it's a positive value in front of the x squared, then the parabola opens upwards. Now, we'll start by graphing very basic ones, where all we'll do is simply reflect it or non-reflect it and also stretch it vertically or shrink it vertically. Today, however, we're going to describe a vertical stretch as a narrower function of x squared. So we stretch it vertically, we're making it narrower to the function of x squared. And that's the result of multiplying by a factor greater than 1. If we multiply by a factor less than 1, then we end up again shrinking it vertically, moving the points farther away from the y-axis, as you see right here. These points are farther away from the y-axis. As a result, you see that this graph is wider than the function of x squared. And that's how we're going to be describing today's functions. So let's look at some examples of this. Here, to graph this function here, let's look at the transformation. Well, we can see that this function, let me make my pens different. We can see that this function is being multiplied by 1/3. It's not negative 1/3, simply basic positive 1/3. So because of this, g of x is going to be wider than the function of x squared. Now, since 1/3 is a positive, this is not going to be reflected across the x-axis. So g is not reflected. So let's graph this. Well, the way we're going to graph this here is going to use, again, a table of values. And we're going to start by picking values of x again. In this situation, since we're making it wider, we're going to pick values of x again that are divisible by the denominator. So for example, like -6, 3, -3, 0, of course, because 0 is divisible by anything, +3, and +6. And with our handy dandy calculator here, we're going to multiply 1/3. This is RTI in Spider, so I'm going to write 1/3, and in parentheses, I'm going to type in -6, and then raise that to the second power. And that equals to 12. Now I get 1/3 and multiplied with -3 to the second power. That equals to 3. If I plug in 0, that's going to equal to 0. 1/3 times 0, even if I raise it to the second power, it's still going to be 0. And because, again, my parabolas are symmetrical to the y-axis, it's an even function, symmetrical to the y-axis, these points are going to match up also. So when x is equal to +3, the y value is also going to be 3. And just like here, when x is equal to -6 and +6, we're going to have the exact same y value. So +12. So let's plot these points on our graph. We won't be able to plot -6, 12 because, well, our highest point here is 10, but we can definitely plot -3, +3, 0, 0, and +3, +3. And again, because of the symmetry, we know, again, because it's symmetrical to the y-axis, we know that the left and right side are going to match up perfectly. $12 should be somewhere up there. So 10, 12, so something around up there. So we connect those points. Our quadratic is going to look like this. So let's look at our next example. On this example right here, notice that we're multiplying by a negative. So that's going to reflect. So G is reflected over the x-axis. And because we're multiplying by 2, G is going to be closer to the y-axis. It's going to stretch it vertically, making it closer to the y-axis, which is thinner. So G is narrower than the function x squared. And in this situation, since we're making it narrower, we'll use only the numbers -2, -1, 0, 1, and 2. We'll probably just end up being able to only graph these points here, right there, those three right there, close to the origin, because these values, because of the narrowness, the stretch that we're making, is going to be, again, too high in order to plot. But we'll see right now. So let's break out the handy dandy calculator, and we have -2. We're going to multiply that with -2 to the second power, which is equal to -8. Now -2 times -1 to the second power, that's equal to -2. And because of the symmetry, the x value of 1 and the x value of 2 have the same y values as negative and positive, -1 and -2. And of course, 0 is going to give us 0. 2 times 0 is 0. Doesn't matter that we raise it to the second power, it's still going to give us 0. So let's plot this. So -2, -8, I'm sorry. -1, -2, 0, 0, and again the symmetry. And there is your graph. And as you can tell, again, it's kind of hard to see because it's upside down, but you can kind of tell that it is in fact skinnier. These y values here are in fact a little bit closer. These points here are in fact a little bit closer to the y-axis than they are over here. Okay, right here, the point again, and at this point, that's 2. Oh, here it is. It's been stretched up to 8. So they are a little bit closer. Look at 8. Look how far away the height of 8 these points are. They're further away than here. They're only 2 units away from the y-axis. Let's see. Let's look at another example. Here again, we have a vertical stretch. So G is narrower than x squared, and G is not reflected. So it's not reflected over the x-axis. And to plot this, let's again use +1 and +2, the same 5 x's that we used last time. So let's break our handy dandy calculator. This time we're going to multiply by 3. That's 12. That's 3, 0, 3, and 12. So let's plot these points. -1, 3, 0, 0, 1, 3, and -2, 12, +2, 12. So and yep, you see again it's skinnier and it's not reflected. The last example, because of the negative sign, G is reflected over the x-axis, and because we're multiplying by 1/4, G is wider than x squared. And here I'm going to use points that are divisible by 4. Since we're making it wider, we'll use values. Okay, that was weird. All right, we're going to use values of x that are divisible by 4. So -8, -4, of course 0, +4, and +8. So -1/4 is written as -1 divided by 4, and we're going to replace the x with -8. That's equal to -16, which means this is +16. And that's equal to -4, which means that this is positive -4 as well. -16 down here. Okay, so let's graph this. So let's see, -4, -4, 0, 0, 0, 4. A little bit more curvy there. So there we go. So this is what the graph will look like. Again, wider and not reflected across the x-axis. Now let's look at some more quadratics in a different format. Now the standard way of writing a quadratic function is in this vertex form. This shows you again the stretch and of course the vertex of the stretch and shrink, and of course the vertex of our quadratic. Remember the lesson on, going back into the lesson on transformation, this x minus h squared is referring to your horizontal translation moving to the left or to the right, and the plus k is your vertical translation of moving up or down. Remember, subtracting moves the object, the parabola in this situation, to the right, while adding will move it to the left. Adding the k value moves the parabola upwards, and subtracting a k value will move the parabola downwards. That is the location of that vertex where the line again changes direction. Now the vertex again is going to be the highest or the lowest point depending on whether the graph is opening up or down. And a line, and because it's the vertex in the middle, basically the middle of the parabola, the axis of symmetry, a vertical line cuts that in half, which is referred to as the axis of symmetry. Now, because the axis of symmetry passes through the vertex dividing the parabola in half, then we can figure out this equation, the equation for this, by determining what the vertex is. The x value of the vertex is the equation to this axis of symmetry. So for example, let's say we have this function here in its vertex form, And by the transformation lessons, we know that this parabola is going to be shifted 3 units to the right because of the plus 3 and 1 unit down. So that means that our vertex is going to be located at 3, -1. So let's plot that point, 3, -1. That is our vertex. Because a vertical line cuts our parabola in half, it's going to go through this vertex. So this is essentially the middle point of our parabola. And the equation for this axis of symmetry is the equation x equals, and it's x because it's a vertical line only intersecting the x-axis. We only touch the x-axis at this value of 3. So x is equal to 3. And as you can clearly see again, it matches exactly to the x value of the vertex. Now, a couple other things that we're going to find in order to graph this accurately is that we're going to find again our zeros, our x-intercepts when we cross the x-axis. Well, because we're looking at when we're going to cross the x-axis, notice that every point on this line has 0 for y. Like this point is -8, 0. This is -6, 0, -4, 0, -2, 0, +2, 0, 4, 0, 6, 0, 8, 0, 10, 0, and so on. So, and every single one of these points here, the y value is always 0. And because of that, that's how we're going to figure out our y-intercept, by having our y value, which is this notation here, become 0. So 0 equals the x minus 3 squared minus 1. And we're going to solve the equation for x. I'm just writing the equation backwards. Instead of having the 0 on the left side, I'm going to simply write it on the right side of my x minus 3 squared minus 1. And all I do now is just simply solve this equation. So we're going to solve this equation by first adding 1 to both sides. We're going to take the square root to get rid of the square. And then we're going to add 3 to both sides. And there's two possibilities now. I can get 3 and add 1, which is 4. So one of our intercepts is at 4, 0. Or I can get 3, and the second option is to get 3 and subtract 1, which is 2. So we're going to cross the x-axis at +2 and at +4. And you know what? Let me do those in red. 4, 0, 2, 0. And notice how those 2 points, those 2 red dots, are always they're in this situation are 1 unit away from, again, the axis of symmetry. Because, again, it's symmetrical. The left side is going to be symmetrical to the right side. It's going to be a mirror image of that. So if this point is 1 unit away from this vertical line, then the other 0, the other x-intercept also has to be 1 unit away again from that line there. Now, let's find now the y-intercept. Well, to find the y-intercept, we're looking for when we're going to cross this line right here. And you'll notice that every point on this line, the x value is 0. Like this point, the coordinate is 0, 10. This is 0, 8, 0, 6, 0, 4, 0, 2, 0, -2, 0, -4, 0, -6, 0, -8, and so on. So every single one of these points and everything in between that I didn't consider has the coordinate format of 0 and then the value of y. So our y-intercept is simply found by now replacing the x coordinate with 0. So here we make x equal to 0. Instead of making the whole value y 0 and solving an equation, we're going to simply replace the x coordinate with 0. And here we can do this a lot quicker just by simply plugging into our calculator. So let's type that in. So in parentheses, we have 0 minus 3 squared minus 1, and that's equal to 8. So f of 0 is 8, which means that our y-intercept is the coordinate 0, 8. And let's plot that in green. So that's right there. And because this graph is symmetrical, that means that on the other side, which is 3 units away from the axis of symmetry, there's going to be another point that's also 3 units away from the axis of symmetry. And connecting the left side from the axis of symmetry and the right side, our parabola is going to look like this. Let's practice one more. So pause the video, find again your vertex, your axis of symmetry, your x-intercepts, and your y-intercepts, and then plot them all on the graph. And then come unpause it and check your work. So let's check your work. So first of all, our x-intercept, because we're adding 5, that's going to shift the graph 5 units to the left, and the plus 8 shifts it up 8. So our vertex is at -5, 8. That means that our axis of symmetry is the vertical line x is equal to -5. So let me first plot my vertex at -5, 8. Our vertex is at -5, which is this vertical line here. Our x-intercept is when y is equal to 0. So I'm going to make this equal to 0. We end up with 0 equals -2x, -2 times x plus 5 squared plus 8. So -2 times x plus 5 squared plus 8 equals 0. So to solve this equation, we start by first getting rid of the plus 8. So we're going to subtract 8 from both sides. Now, we cannot distribute the -2 inside here because of the square. So instead of trying to multiply it in, we're going to do the inverse operation and divide both sides by -2. And that's going to reduce this value right here. I had a question in one of my classes that they're asking, do we divide this number by the 2 as well? No, only this one right here. We're dividing by 2 specifically because we're multiplying by 2. So these two things is what's going to reduce out. And we're going to be left with x plus 5 squared equals 4. And now we can take the square roots to both sides. And x plus 5 equals to both positive and -2. Let's continue over here. Now here I just have to then get rid of the 5. So I'm going to subtract 5 from both sides. And I get my value for x. So x has 2 possibilities. Our 2 intercepts are the following. The first possibility is that if I add -5 with 2, that's -3. So -3 is 0. Second possibility is if I subtract -5 with 2. So -5 minus 2, that's -7. So -7, 0. And we're going to do this in red. So let's plot both of these. And again, look, our axis of symmetry. Notice how this red point and this red point are symmetrical to each other. They're both 2 units away from the axis of symmetry. Now let's find our y-intercept. So here we get our y-intercept by now having the x equal to 0. And with our handy dandy calculator, with our handy dandy 84, we can just simply do this all in one step. So -2 parentheses 0 plus 5 squared plus 8. I know some of the keys look a little bit differently, but this is again the same setup as the 84 that we use in class. Some of the keys look a little bit differently, but it's the same thing. And we end up with negative 42. So our y-intercept is 0, negative 42. And we can't plot that one. That one cannot be plotted because we're going to go all the way down. We only go down to a lower negative 10. But in terms of when we get there, we'll notice again that that value is going to be 1, 2, 3, 4, 5 units away. So there'll be another, again, going down 42 from here, going down 42 units from here, from the y-axis all the way down to negative 42. We're going to get a point again that's symmetrical to that there. So this is what our parabola is going to look like right now. And there you have it. So that concludes again the examples on lesson 2.1, graphing quadratic functions. If you have any questions, please send me a message or remind or through email. And like always, I appreciate you watching, and I hope you have a great night.